Good morning, everyone. My name is Mehdi Tavakoli, and today I will be presenting on the Crustal architecture of the Atikokan Transect. This project is part of the Metallers and is conducted with collaboration with co-authors. The focus of this project is to integrate seismic data, magnetic data, and field data to better understanding about the structural evolution that we have. That we have in the Atikokan area to have a better understanding of the structural evolution in the Atikokan area. Yeah. Thank you. Atikokan area is located in the Western Superior province, about the 175 kilometers west of the Thunder Bay, as you can see in the red rectangle. And Atikokan Transect, it's in blue line. Here was acquired by the Metallers, and we just used three previous available seismic data from the LithoPro project, as you can see here, to interpret them to have a better understanding of the regional tectonics in this area. The distance between the Atikokan transects and the LithoPro profiles is about 75 kilometers. Here is the geological map of the Atikokan area. You can see the Koitiko fault as a east-west trending major transcurrent fault between the two sub-provinces. On the north, we have some greenstone belts that most of them are belong to Mesoarcheans, more than 2.9 billion years ago. And there is a Marmion batholiths with the 3 billion years ago. And but in the south of the Koitiko fault, we have exposure of the Koitiko basins that are belong to the Neoarcheans. This is the position of the seismic lines, and the star shows the MTS stations. This study aims to answer three main questions. The first is that what do seismic and MT data reveal about the deep crustal architecture in the Atikokan area? The second is what is the subsurface geometry of the Koitiko fault as one of the major structural lineament that we have in this area. And the third is how do structural field observations correlate with the geophysical data and visual interpretation that we have in this area. On the left, you can see uninterpreted sections of the Atikokan transects. On the right, sorry. On the left, you can see the interpreted sections. These parts belong to the Koitiko basins as a metasedimentary volcanic metasedimentary rocks that we have. But these parts belong to the Marmion terrain. Most of them mafic and metamafic volcanic rocks belongs to the greenstone belts. We have, for example, here steep rock greenstone belts, Finlayson Lake greenstone belts here, Marmion batholiths, and so on. We have a flat reflector, seismic reflectors here in this area. We interpret it as a Moho boundary. And below of this, we have lithospheric mantle. But above of this, you can see in the two area, we have a good continuity of the reflectors, one of them in this area and another in this area. And there is a relatively poor data in the middle part. And if you can see the Koitiko fault between the two sub-provinces that we have. It is the lithospheric fault here, you can see that. There's a very sharp cutting the reflectors. Based on the reflector quality, continuity, and the deep directions of the reflectors, we just separated and divided the Atikokan seismic profile into 8 zones. The zone A just mentions that the lithospheric mantle, Moho boundary. Zone B, C, D, and E could be related to the lower crust. Zone C, as I mentioned, is a poor data. We have poor data here. And it could be compatible with the inverted magnetoid modeled data that is overlaid on the seismic here. You can see that zone C. And they have a, high conductivity data here. Maybe it could be related to the intrusions, magma intrusions. And you can see another high conductivity of the data as a C3 here. It's beneath of the Marmion batholiths, maybe related to this. And these two high conductivity zones maybe are sub-vertical, so somehow sub-vertical, related to the maybe magma intrusions in that area in the lower crust. And two high resistivity zones. This one is related to the critical metasedimentary rocks that we have, and this one related to some plutons that belongs to the Neoarchean here. We just put these two transects. The upper is the Atikokan transects. The scale is the same, and the position I tried to show the right position based on these two parallel transects that we had in this area. At the bottom, you can see the merge of the three seismic sections that I showed you at the first slide, their position. These three, we just merge manually these three seismic profile to show them what is the structural complexity we have in this area. And the Atikokan transect is somehow related to this part. You can see some of the reflectors in the middle crust that is compatible with the reflectors that we had on the profiles. And even you can see here, it's compatible with the critical fault here. On the top, these uninterpreted lithotrope seismic profiles. On the bottom is interpreted. We interpreted these profiles. And you can see that there's a relatively flat reflectors that could be related to the Moho. Its depth is near to 40 here, 40 kilometers, I mean. And there is some down-dipping reflectors. I mean, the north-dipping reflectors here may be related to the remnant of a subducted slab. But as you can see, these sections could be divided in two major parts. One of them is related to the lower crust that we have in this area, and another related to the middle crust that we have in this area. You can see that the complex structures that we have beneath in the lower crust, beneath of the Winnipeg River trains and Marmion trains here, we can see the stack of the imbricated thrust and duplexes that we have in this area, very complicated in this area. But beneath of the Koitiko and the Wawa, there is a simple imbricated thrust that the depth of this thrust decrease toward the source. And you can see some of the complex thrusted zones in the Winnipeg River, that it could be part of the lower middle crust. And this is the position of the Koitiko fault. As you can see, Koitiko fault is a deep-seated, low-angle thrust fault, and it's originated as a thrust fault. And after that, you can see it extends to sub-vertical near surface, as you can see between the two major provinces that we have on the field. Here, I put the two interpreted sections to have a good compare to each other. You can see in this area. We interpreted these thrust faults as the ductile thrust fault shear zones that we have in this area we have the same, and the boundary between the middle and lower crust as a blue lines, you can see here, we just put here, and the middle crust the same. It's very clear that these two sections are very similar to each other. Also, we have a 75 kilometers distance between these two lines. Here is the Atikokan area aeromagnetic data that we have. On the left, you can see total aeromagnetic anomaly. This is the Marmion bathylites here, and it's clearly could be detectable. Finlayson Lake, Crustal belt, something like this. And you can see the critical fault very easily and detectable as a major transcurrent fault that we have in this area. And you can see in the critical basins some east-west trending of the plutons that intruded in this area. All of these things are parallel to the critical fault and parallel to the subductile thrust sheets that we had beneath of this area. No, so far we just talked about the geophysical data, but now we shift to the field data. On the critical basin, we have just some bedding and parallel bedding foliations, and that are somehow east-west trending. The mean orientation of this is somehow near to the 270, as you can see here. And some of the other evidences we have, for example, access of the tight folding in the quartz veins. Bedding parallel foliation is one here, for example, or here, woodings of the quartz veins, that their axis is perpendicular to the shortening. So these data are is consistent with the NS shortening direction that is resulted from the thrusting as seen in the seismic sections. Here is another type of the data we have in the critical basin. This data shows the dextral shear sense indicators, dextral shear sensing and movement in this area. For example, here we have some dextral and echelon quartz vein. Here you can see that a strange shadow that shows the right lateral shear sense indicators is clearly here. Or here you can see that dextrally sheared quartz veins. These data are somehow related to the another foliations. This shows these S2 foliations. These foliations has a change, in the shortening direction, shows a change in the shortening direction, about 15 degrees related to the primary shortening that we have. So these data are consistent with the dextral reactivation of the critical fault due to the change in the shortening direction. So we just moved on the critical fault, exact on the critical fault field data. Here you can see some SC fabrics. These C planes or C fabrics are parallel to the shear planes that we have. Some shear bands, C prime here, it's easily detectable. And some myelonitic foliations, S2 here. And this data shows that these data could be related to the S2, because these two are very similar to the other data we just plotted as it is S2. So as a result, the seismic and MT data define major crustal boundaries. Deep imbricated thrust faults that we have in this area and duplexes we can see in the beneath of the Winnipeg River and the Marmion indicate a complex tectonic evolution. Seismic profiles reveal that the critical fault originally formed as a deep-seated thrust fault, which steepens to subvertical near surface. And during the thrusting, a bedding parallel foliation S1, as I shown, formed in the Koitiko Basin. And finally, the Koitiko fault evolved into a dextral transcurrent fault with the development of the second regional foliations, S2 in the Koitiko Basin. I want to have a special thanks to Dominic Friesen, my field assistant during the summer 2024. Many thanks to Natalie, Courtney, Puran for managing field logistics and the GIS database. Thanks to Agnico Eagle for granting access to their properties. Thank you.